All right, let's dive right into this explainer. Today, we're literally unpacking the exact mechanics of Ceph, a truly massive, masterless distributed storage system. If you've ever wondered how modern infrastructure manages to scale up without just breaking apart, well, we're going to figure out exactly how this works. I mean, just think about the sheer mind-boggling scale of data today. How do you actually store an exabyte of data without the entire system completely collapsing under its own weight? Because when you're processing billions of file updates concurrently, traditional storage designs hit a hard physical limit. The stakes here are immense, and honestly, the classic ways of doing things simply cannot keep up anymore. Here is our roadmap for the explainer. We'll hit the centralized metadata wall first, then look at Ceph's Masterless paradigm. After that, we'll cover the BlueStore engine, the gossip mesh, the life of a query, and finally wrap up with durability and self-healing. Let's get into it. Section 1, the centralized metadata wall, breaking the limits. So to really appreciate the genius of Ceph's solution, we've got to understand our technical villain first. Let's think about the classic centralized architecture. Every single time a client wants to read or write a file, it has to ask a central master, hey, where is this data? This creates massive single lock contention and severe RAM limits purely because that lookup map grows linearly with your data. Eventually, your central indexing catalog completely saturates. But under Ceph's masterless strategy, the client uses its own local CPU to mathematically calculate where data lives. That means zero lookup saturation. It basically boils down to maps versus math. The old centralized premise is like asking a central librarian, a database, where every single piece of data lives. And eventually, that poor, overworked librarian simply collapses under the sheer volume of requests. Ceph, on the other hand, relies entirely on math. It offloads all metadata allocation directly to the client's local CPU using an algorithm, completely bypassing those network lookup gates. It's a total paradigm shift. Section 2, Ceph's radically masterless paradigm, the power of math. Now, this massive shift didn't just happen overnight, right? It actually traces all the way back to 2004 as Sage Whale's PhD thesis at UC Santa Cruz, which was aimed at eliminating these massive bottlenecks. By 2006, the foundational CRUSH algorithm, which stands for Controlled Replication under Scalable Hashing, was officially published. Fast forward to 2017, the massive BlueStore user space engine went generally available, followed by natively encrypted protocols in 2019. It's been this steady, really fascinating march toward enterprise-grade efficiency. Moving on to Section 3, BlueStore User Space Storage Engine, direct to disk. So we're dropping down to the physical hardware layer here to see how Ceph actually writes data to standard unformatted drives. Traditional engines slap data on top of standard POSIX file systems like ext4, but that forces every single read and write to traverse the Linux kernel virtual file system, or VFS, which causes brutal CPU context switching and double journaling. Enter O_direct DMA. This is absolutely crucial. BlueStore essentially opens raw, unformatted block devices and streams bytes directly to the disk. By bypassing the kernel VFS and page caches entirely, it frees up 100% of node RAM for user space operations and completely eliminates that double writing bottleneck. And what's really cool is how BlueStore handles different workloads by literally splitting its write pathway in two. For large multi-megabyte writes, the raw payload bypasses the write-ahead log entirely, streaming directly to unformatted disk blocks via that O_direct DMA we just talked about. That maximizes pure throughput. Conversely, for small kilobyte range writes, writing straight to disk would cause massive performance drops. So instead, the deferred path packages these tiny payloads and commits them instantly to a high-speed RocksDB write-ahead log on a flash SSD. A background thread later consolidates and flushes them cleanly. It's this perfect dual-engine design, optimizing both bandwidth and IOPS at the same time. All right, Section 4, Gossip Mesh and Paxos-backed, decentralized consensus. Let's step up to the network layer. How do all these isolated masterless nodes, what we call object storage daemons, or OSDs, actually coordinate globally without a boss telling them what to do? Well, every OSD daemon maintains continuous, non-blocking UDP heartbeat checks directly with its active peer neighbors. And why UDP? Because it bypasses heavy socket lock queues. If an OSD goes down, its neighbor instantly detects the failure. It locks the status and gossips the offline failure report downstream to all other peers while notifying the monitor cluster. The nodes then dynamically adapt their local CRUSH routing map on the fly, completely avoiding central lookup servers. Now, I just mentioned the monitor cluster, or MONs. But wait a second, didn't I just say Ceph is masterless? Yes, absolutely, because these Paxos monitors are incredibly lightweight. They do not hold file indexes or block handles. Instead, they simply serialize highly compact incremental epoch updates across high-level maps like the MON map, OSND map, PG map, and the Crush map. They track global membership and failure domains, not individual files. Clients just cache these maps once and do all the math locally. Section 5. The life of a query. Chronological read and write pipelines. Let's slow the pace down for a second and trace the actual chronological journey of a single byte moving through this architecture. Say a guest virtual machine wants to write to a 100 GB virtual disk. Phase 1 is block slicing. The client automatically slices the virtual drive into uniform 4 MB write as storage objects. 2. Crush target resolution. The client hashes the object ID and executes the crush math locally to find the target physical OSDs. 3. Direct stream. It establishes a raw TCP connection directly to the primary OSD. 4. Replica cascade. The primary OSD multicasts the payload concurrently to its replica nodes. And finally, 5. User space commit. The data is written straight to raw disk using BlueStore DMA, and the metadata is indexed in RocksDB. To really lock in that end-to-end flow, keep in mind that the client runs the CRush math totally locally. There's no monitor lookup required at all. It targets its primary OSD and sends the payload via a direct raw TCP connection. The primary OSD then takes over the replication, multicasting to its replica OSDs. They write directly to raw disk, index in RocksDB, and return an acknowledgement. Once the primary gets the ACKs from the replicas, it confirms success back to the client. The control plane monitors are completely bypassed during this entire data transfer. It's just incredibly elegant. Section 6. Durability and self-healing. Protecting the exabyte. Because, let's be real, at the exabyte scale, it is never a matter of if hardware will fail, but when and how often. So think about this for a second. What actually happens when a physical disk rots? We aren't just talking about a drive completely dying and smoking out of a server rack. We are talking about silent data corruption, where a flipped bit degrades a file without ever throwing a hardware error. This is a massive threat when you are storing billions of objects. This is where the read path absolutely saves the day. When a client requests a read, it connects directly to the primary OSD. The OSD queries RocksDB for the exact physical sector and issues an async DMA read. But instead of blindly returning the data, the OSD calculates a checksum on the fly. If bit rot is detected, it transparently pauses, reaches out to a healthy replica in the background, pulls the clean blocks, serves the verified data to the client, and heals its own corrupted sector automatically. Let's break down those exact steps, because honestly, this is where Ceph is a total game changer. BlueStore calculates a dynamic CRC32C checksum right in volatile memory. It compares this against the golden checksum it originally recorded in RocksDB during the write phase. A mismatch instantly detects the silent hardware bit rot. It holds the network transmission to the client, keeping the corruption isolated. It then automatically pulls a clean replica block via the peer network. Finally, it transmits the clean data to the client while simultaneously background healing the local physical sector. All of this transparently intercepts bit rot without a single central map intervention. Which brings us to the ultimate disruption that Ceph brings to distributed storage. We've seen exactly how maps replace maps, how local CPU calculation completely replaces central bottleneck lookups, and how nodes peer and heal themselves dynamically. So I'm going to leave you with this. If algorithms can dynamically route, heal, and scale an exabyte of data with zero central authority, is centralized master control literally just a legacy of the past? Definitely think about that as you consider the future of infrastructure. Thanks for diving deep with me on this explainer today, and keep learning.